Alright, so after spending some time with the previous lesson doing factoring with algebra tiles, we're going to try look a different method for factoring that hopefully won't have us be using tiles. Because as we know, there's limitations using the tiles, right? If you have large numbers or fractions, tiles really just aren't ideal. So what I asked you to do when you were finished with all your factoring yesterday was take all your examples and record your results into an array and to look for patterns that you may be able to see in your array that might help us factor this a little bit faster. So I put results for the first three here. And let's just see what we can find here. Now, remember when we were using tiles, when we set up our trays, we put x squareds in the top left of our tray. We put our constants in the bottom right of the tray. And what we were trying to figure out was how to arrange x tiles to get the factoring to work out. So, the big challenge is to try and get the x tiles to work out. Now, looking at this here, with all these cases here, we're trying to look for a connection here between what we get for our x values inside the array and the original function. So maybe you saw a pattern, maybe you didn't, but you might notice here that if you look at the values here, the coefficients of x inside the array, we have 4 and 2. Well, we know that in the array, these two numbers here have to add to give us the 6x that we have here. Okay, so and that's going to be the case for all of them. So in B here, we have 2x minus x to give us 1x. Here in C, the 2x terms should add up to minus 5x, and they do, because we have minus 3x and minus 2x, and in D we have 3x and 3x. So there's a little bit of pattern there with our x tiles. And do you notice anything else? Hopefully you might have noticed here that if you look at the multiplication, if you do 4 times 2, you wind up with 8. And where do you see 8 in the equation? Well, it happens to be our constant term right here. Okay, let's see if that works for all the other ones. If we're looking for coefficients of x in B, we have 2 and negative 1. 2 times negative 1 is negative 2, which is the C value right there. In C, negative 3 times negative 2 gives me positive 6, which is, again, that value right there. And you see this continuing, right? 3 times 3 here is 9, which again is our C value. So in general, our x terms inside this array, they need to add to give us our B value here, our coefficient of x, but they have to multiply to give us our constant or our C value. So looking at the other ones, I know these are ones you've already done. Let's see if that pattern holds. So for E, you would need two numbers that multiply to negative 6, but add to positive 1, the coefficient of your x term. Because remember, in our array, we'd have our x squareds in the top left, our minus 6 in the bottom right. So what two numbers are going to multiply negative 6 and add to 1? Well, that's going to be positive 3 and negative 2. And so once you find those two numbers, we wind up with 3x and minus 2x in the array, because again, 3x and minus 2x add to 1, but multiply to give us the negative 6, the coefficients do anyways. So now we can try to figure out what goes on the outside of our array. So for x squared here, the only combination that multiplies to x squared is x and x. Okay, and then we can fill in the rest of the array by thinking, okay, if I have x here and I have minus 2x down here, x times what gives me minus 2x? Well, it has to be minus 2. Okay, over here in the top right corner, x times what gives me 3x? It's going to be plus 3. So my factored form is x plus 3, x minus 2. Okay, let's try and look at one other one just to be sure. So let's try looking at f. So with f, we have x squared minus 3x minus 10. So I'm going to take my x squared, put in the top left, my minus 10, put in the bottom right. And here I'd be looking for two numbers that would multiply to give me negative 10. So multiply to my C value, but add to my B value, which in this case is negative 3. Okay, so with a little bit of playing around with it, you might be able to see that these two numbers that work are going to be negative 5 and positive 2. So that gives me my x terms inside the array, negative 5x and 2x. Okay, and then I can figure out what goes on the outside. So x times x gives me x squared. Okay, x times negative 5 gives me negative 5x. And x times positive 2 gives me 2x. So I'm going to wind up with a factor form of x minus 5, x plus 2. Okay, so this pattern seems to work. Let's see if it works for all the other examples here. So let's keep going. And here's some other ones that you worked on yesterday. So if you look at I, x squared minus 4, in this situation, once we put our x squared and our constant, our minus 4 in here, you'd be looking for two numbers that multiply to our C value, which is negative 4. And in this case, our B value, because there is no x term, is actually 0. So we have two numbers that multiply to negative 4 add to 0. Well, those two numbers are going to be 2 and negative 2. So that gives me 2x and minus 2x. So it winds up on the outside factoring into x minus 2 and x plus 2. Okay, so the pattern does still seem to work. Okay, let's try one that's a bit more complicated. Let's take a look at k. So what I'm going to have you do is, again, write in your results for the array that you had when you factored this using algebra tiles. And let's see if that pattern that we just discovered, where the two numbers multiply to our c value and add to our b value still works. Okay, so there you had, should have looked something like this. So let's see if that works. So again, we started with putting our x squared terms in the top left and our constant terms in the bottom right. Now, let's see. So for our x terms that we wound up with, we had 6x and x. So those add to 7x. That makes sense. So they add to our b value. But 6 times 1 do not multiply to 2. So all of a sudden, this pattern seems to fall apart, the one that we thought would work for all of the first 10 examples. So let's think about this for a sec and see if there might be some kind of way around this. What was different about this one compared to all the other ones we just did was looking at the x squared. There was a coefficient of x squared that wasn't 1. Okay, so the coefficient of x squared was 3 in this case. Well, one thing you might notice here, if you look at the coefficients of there on the diagonal here between the 3x squared and the plus 2, the coefficients are 3 and 2, and those multiply to 6. So 3 times 2 gives me 6. Well, it happens to be the exact same value you get when you multiply the coefficients along the other diagonal. So here, if you look at our coefficients of x, we have 6x and 1x. So 6 times 1 gives me 6, which is the exact same thing as 3 times 2. Okay, so it seems to be the case here now they have to multiply to the same value as a times c, so in this case 3 times 2, which is 6, and still add to 7. Okay, and if you think about it, that actually, if this pattern is true, that's still true for the other ones we just did, because all these examples we looked at over here, the coefficient here on x squared was 1. So if we look at the coefficients here, 1 times 8 is 8. It's still the same thing as 4 times 2. So the idea still holds, it's just it never came into play with the other examples because the coefficient of x squared was always 1. So in general, it looks like that what we're looking for are two numbers that multiply to a times c, in this case 3 times 2, but add to 7. So in this case, the two numbers were 6 and 1, which is what gave us the 6x and 1x in the array. And then we could work out what's on the outside. Let's see if let's try it for L. So if we have L, I'm going to put my 2x squared and my minus 1. Okay, and I know this one you've already done, but let's see if we can look at it again, trying to just use arrays without using algebra tiles. So we'll be looking for two numbers that multiply to, again, a times c. So 2 times negative 1, which is negative 2. Okay, the numbers need to also add to my x term, which has a coefficient of 1. So two numbers that multiply to negative 2 and add to 1. So these two numbers are going to be positive 2 and negative 1. So that tells me in my array I'm going to get 2x in one corner, and minus 1x, or just minus x in the other corner. And just like before, I can now figure out what goes on the outside of the array. Now this one can be a little bit more complicated because with all the ones we did on this page, we always had just 1x squared in the top left of the array. So it was always just x times x, every single example. Here there's actually some options here because for 2x squared, you're going to have 2x and 1x. So you got to think about where you have to put the 2x and 1x. Let's just say, for example, I wasn't thinking ahead, and I put the 2x here and the x here. So again, 2 times x to get 2x squared. Well, now I'm going to run into a bit of a problem because if I want to try and fill in what goes in down here on the bottom left on the outside of the array, I'd have 2x times something to give me negative x. And 2 does not go into negative 1 evenly. You're going to get a fraction or a decimal, and we don't want that. Okay, we want to have whole numbers for our values on the outside of the array. So if I have 2x here, it's not going to work. So instead of trying 2x in this corner and x over here, I'm actually going to switch those around. Okay, so I'm going to try 2x here and x up here. And now let's try it. So 2x times what gives me 2x? Well, it's just going to be positive 1. And x times what gives me negative x? That's going to be minus 1. So I wind up with, for my factored form, 2x minus 1, x plus 1. Okay, so this rule seems to work. It's just going to be a little bit more complicated to try and figure out what goes on the outside of the array, but this will help us get our x values inside the array. Okay, so let's summarize this. So in general, for any quadratic of the form ax squared plus bx plus c, so something in standard form, if we look along one diagonal, again putting our x squared terms in the top left, our constants in the bottom right, if you're looking at just the coefficients, the a and the c, when you multiply those together, you're going to get, of course, ac. Now, what we're trying to figure out, again, just to remind ourselves here, is what's going to go in this section of the array. There's going to be some values of x, some coefficients. And what those coefficients are, well, whatever they are, they're going to add to the b value, because we know that these two values have to add to give us the x term, but they also multiply to a times c as well. It's the same value as the multiplying the coefficients on the other diagonal. So that's going to help you solve any of these trinomials that you want to factor. Okay, so let's actually try and put this to use. Okay, so I'll go through these with you guys, because then you're going to have a lot of practice to do on your own afterwards. So looking at the first one here, x squared plus 12x plus 11. Okay, it just makes a bit more space here. I'm going to set up my array first. So as a rule, I recommend that you always start by looking for a greatest common factor. So this one has none. But once you have that greatest common factor taken out, you're going to put your x squared term in the top left, your 1's, your constant in the bottom right, and then try and figure out what the coefficients of x are going to be in the other corners of the array. Okay, so we have an a value of 1, a c value of 11, so we need two numbers that multiply to 1 times 11, which is 11, but add to my x term, which is 12. Okay, so those two numbers are going to be 11 and 1. So I'm going to put 11x in one array, one corner of the array, x in the other. If you switch the x and the 11x, it's not the end of the world, because it'll work either way. It's just a matter of your preference. So now I can figure out what goes on the outside. So if I'm multiplying to x squared, the only options are to have x and x. So now x times what gives me 11x? I can fill in this part up here. It's going to be plus 11, and x times plus 1 gives me just x. So my factor form is going to be x plus 1, x plus 11. Okay, let's take a look at the next one. So, just like before, look for a common factor first. I don't see one. Put my x squareds in the top left, constants in the bottom right. So I need two numbers here that multiply to a times c, so 16 times negative 1, negative 16. Okay, and they add to my x term, which in this case is 0, because there is no x term. So two numbers multiply to negative 16, add to 0. If they add to 0, they have to be equal in magnitude, but one positive, one negative. 16 is a perfect square, so you wind up with 4 and negative 4. So that tells me it goes up here in my array. Okay, now for 16x squared, it can be a little bit more complicated here, because there's lots of things that multiply to 16. There's 1 and 16, 8 and 2, 4 and 4. But you can see what would happen here if I picked the wrong one. Let's say I tried to pick, for example, 8x and 2x. Okay, I wouldn't be able to finish this one up here, because if I try and put in 8x, I'd have to have some sort of fraction up here to try and get things to work out, and I don't want that. So 8x and 2x won't work in any combination. Even if I switch these, I'd still be trying to put 8 into 4 down here, which is not possible. Okay, you run into a similar problem if you try to do 16x and 1x. So the one that's actually going to work here is going to be 4x and 4x. Okay, so 4x times what gives me negative 4x? Negative 1. And 4x times plus 1 gives me 4x. So this becomes 4x plus 1, 4x minus 1. Okay. Now, you might notice here, just to briefly discuss this, if you look at the first term here, the a value is a perfect square. Okay, and we have 16x squared. The c value 1 is also a perfect square, and they're being subtracted. So this pattern is actually called a difference of squares, and I call it that because we have a perfect square minus a perfect square. And you might see a certain pattern with the final answer. When you go through the actual handout later, you're going to see a few more examples of difference of squares. You might be able to recognize a pattern to help you go through those a bit quicker. Okay, so we're actually going to continue this over in part 2. I'll do the last few examples with you guys and give you a chance to practice. Okay, so we'll see you over there.